Hi there. The purpose of today's video lesson is to review topics or concepts related to investments. The context of this particular lesson is after students have studied geometric sequences and geometric series. So the assumption here is you'll know all about the general term for geometric sequence, and you'll know about how to find the sum of n terms of a geometric series. So those are all prior knowledge for this particular video. So what we should try to do when learning new things is to connect things we've learned before. And one of the things I learned before was that geometric sequences are defined as u sub 1, or n rather, is equal to the initial term u sub 1 times some common ratio to the n minus 1. And so the comparison between these two, first the P represents principal investment. That corresponds to U sub 1, which would be our first term of the geometric sequence. In a geometric sequence, we have one R value as the base of the exponential. And for investment, in order to get the appropriate base of our exponential, we need 100% of the investment, plus we need the interest rate added on. So that's the extra bonus interest. I'll explain what the n is about in just a little bit, but the only other difference in comparison between these two is that here we start with t equals 0 to get the principal investment. So in other words, when we work with investment, we assume that the money is put in at the very, very beginning of the year, and then at the end of one full year, we've now accrued interest. So when you put in t equals 1, you will get the second term of this particular sequence. Nonetheless, if you can at least look at how the structure is the same, it's a starting value, a rate, and then an exponent, a starting value, a rate, and then an exponent. You can use the same headspace to talk about investments as you do when you talk about geometric sequences. The other difference, though, has to do with compounding, and it's the number of compounding terms that we talk about. So basically, somebody said, well, instead of waiting an entire year to get interest, why don't we give a fraction of the interest a certain number of times a year? So to understand this n and what it means and how it's used, I want to look at a specific example. So we're going to keep a few things constant. We're going to invest $100. We're going to invest for 5 years, and we're going to invest at a 4% interest rate. The only difference we're going to change here is when we compound. We can compound annually, quarterly, or monthly. There are other ways to compound. You can compound daily, and there's even continuously. But for the purposes of this video, we'll just look at how the n, or the number of compounding periods, factors into our geometric sequence for investment. For annually, all I have to do is take the formula as written and let n equal 1, because that means in 1 year there's one compounding period. So in other words, the formula, if you're not going to worry about compound interest, if you're only going to compound annually, just making n equal to 1 is just going to be the principal investment, 1 plus the interest rate to the t power. So you can see here, I just make n equal 1 in both cases, and we get a more simplified formula, and that's what I applied here. Now quarterly, what quarterly compounding means is you're going to take a quarter of the interest rate, but we will apply that interest not once, but 4 times throughout each consecutive year. So in 1 year, we would have 4 compounding events, and in 10 years, we would have 40 compounding events. So that's why we have the n times t in the exponent, because the number of compounding events will determine how many times in a year we are going to achieve that. And the other thing is we divide the rate by n because we're not going to get a full year's worth of interest. We're only going to get a quarter of the interest for a quarter of the year. So to compound quarterly with the same parameters otherwise is to simply take your $100, multiply by 1 plus. We're going to take that 0.04 and divide it by 4 equal parts, and divide it into 4 equal parts, and then we'll do that 4 times for every year. So in a 5-year time, there's 20 compounding events of a quarter interest. Now, so monthly means that 12 times a year, we're going to be doing that interest event, and therefore we would take the same parameters, 0.04. This time, though, we're going to divide by 12, and then 12 times per year, we're going to calculate that interest. So the only difference here is the compounding periods factor into our equation accordingly. It's pretty straightforward, really, really basic. To see the impact here, it's not going to look very significant, but annual compounding, $121.67. Quarterly, we get $122.01, and then we get an extra penny more if we compound monthly instead of quarterly. May not seem significant, but remember, this is a $100 investment for 5 years. If we were to tack a $1 billion investment for 20 years, the change from annual to monthly is going to be a lot more significant than just a couple of pennies. So that's why it matters. It only matters for the rich people. Anyway, that's the basics of using the investment formula and how it relates to geometric sequences. So in practice, you can see here there's, maybe you can't, it's really small, but we got this Victoria is putting 1,500 euros into an account, 4% interest, compounded semi-annually. That's twice a year. And so how much will our account hold in 10 years? So this is straight up plug and chug mathematics. We put the investment here, we put the rate there, and the number of compounding terms here and here. So to find out then after 10 years, we replace t equals 10, and we get 22,000. So that's all there really is. This isn't rocket science. For the second problem, it's the same kind of question. The only difference is we're investing $500. Interest rate is the same, but we're compounding quarterly. And how much is she going to have when she turns 16? So we've got $500. We've got the 4% interest, compounded quarterly, 4 times every year. So at 16 years, she would have $945.23. Again, straightforward. So then all of a sudden they start to throw a little wrench on here. Now they're asking the question how much money should be invested if I want to end up with $4,000 or euros after 6 years. So how is this different from all the other ones? Well, in each case, we're always looking for how much is the account worth after a certain period of time. Now we know how much time is going to be invested. We know the rate, and we know the desired amount. What we don't know is the principal, the p-value. So in order to make 16 work, we're going to have some basic algebra skills, perhaps, or the ability to use technology to solve equations. So actually, in this case, it should be pretty easy. Anyway, so as you can see, everything that I know has been replacing the parameters of my formula, except the p-value, the principal investment, is not known. So all I have to do is figure out what this number is, and it turns out to be that long chain. I kept all the decimals so I get a more accurate result. And then when I divide 4,000 by that number, I will find p, the amount of money needed to be invested. So if this person invests 2,968 euros and 79 cents, then in 6 years' time, there will be $4,000 in that account. So that's just a variation on the theme. 2 more concepts then. Just want to point out that sometimes if they don't mention compounding periods, they just say annual interest, that's when we are going to assume that we're just dealing with the basic geometric sequence. Again, we start with n equals 0, not n equals 1. So after 5 years, the investment is worth $6,786. That's not really a big deal. But for part C, we're asking how long is it going to take for the account to exceed $10,000? And for that, it says write an inequality, so it's simply the amount of the investment should exceed $10,000 if you're reading from right to left. Dividing both sides by 5,000 just to make nicer, cleaner numbers and smaller numbers on my calculator. I am going to enter this into my calculator, use the calculator to find the point of intersection, and then replace it as the solution to the inequality. So in other words, if n is more than 11.34, then the value of the account will be more than 10,000. So to interpret the answer to this question, it said the minimum n value. If n was 11, I would not exceed $10,000 at the beginning of the 11th year. So I have to wait till the end of the 11th year or the beginning of the 12th year in order to be able to guarantee that I exceed the $10,000. So the reason I bring this up in the context is because, again, the variation on the theme, sometimes we'll ask how long will it take, or sometimes we can ask how much should be invested. It's just a matter of swapping out one known parameter for an unknown parameter and going. And as you can see, you can even write and solve inequalities. The other reason for me bringing this up is if you don't have the logarithmic prowess or the pencil and paper method for solving this, it's perfectly fine for this chapter to use intersection from a graphing calculator to solve. So make sure you know how to do that. Finally, I just want to make sure that we connect the relationship between geometric sequences, which the formula for investment is a modified geometric sequence formula. But then there's the concept of the series. And to know how a series is different from a sequence when we talk about investment, you're dealing with a sequence. If you take a certain amount of money and you just let it sit in the account, and then you just wait years and years for it to go by, and then you just say how much money happens to be there now. With the series situation, it's more of what's called an annuity. And in that situation, we're going to put money into an account, and then the next year we're going to put in the same amount, and the next year the same amount. So we're going to keep adding money to the account, but we will also keep adding interest to the account. So what I'm going to show you now is not a full write-up of this problem, but it's just to explain how we talk about investments and interest and adding money to the account over and over and over again. So basically, I just wanted to show you that in the first year, or the 0 year, Samantha has $1,000 put into the account. Now, at the end of that year, she will have 4% interest on that $1,000. So that'll be 1,000 times 1.04. That's how much the account is worth at the end of the year. But she's going to stick in another $1,000. So this is the second year's money and the first year's money added together. Now let's fast forward. 3 years have gone by. So the first year's $1,000 had 4% interest added twice. The second year's $1,000 had 4% interest added, compounded once. And the third year's money, no interest yet. So we can see here that at the beginning of 2012, when this was the beginning of 2010, 3 years later, we had the new money, the money from the second year, and the money from the third year. Hopefully that's enough for you guys to be able to spot that that is in fact a geometric series. Specifically, this is a geometric sequence, and then when we add the value of the account together, we get a series. So unlike geometric sequence problems, when we're dealing with annuities, we should understand we're dealing with a series. But that doesn't change what we know, and that is the sum of a series can be calculated by u sub 1 times r to the n minus 1 over r minus 1. And so that's what I'm employing right here to get the final equation to solve. So this isn't the answer to the question, but just to make sure that you understand, for most investment problems in IB, you're going to see a geometric sequence using our base level formula, the one that is provided in a formula packet. However, they're not going to tell you that there's a formula, but when you're dealing with annuities, you're still going to use geometric sequence space in your mind. But remember, we're going to be adding terms each year, and so we should use our series sum formula rather than our sequence general term formula. So, sorry the video was kind of long, but I hope it's helpful. Have yourselves a great day. Thanks.